Mm, what time is there? 10:57. Okay, 10 minutes are there. The tool materials. Now, before selecting a cutting tool, we need to have better idea of what workpiece I am machining. That is workpiece material I need to consider. Then what are the machining properties expected? Means what surface finish should be there, what accuracy should be there, what are the expected temperature to be generated, what is the relationship between cutting tool and workpiece. Relationship in the sense, is there any chemical affinity between those two? If they are inert against each other, that diffusion and all would be will not be there. But if cutting tool and workpiece has some chemical affinity at either at room temperature or at elevated temperature also, then that diffusion rate is going to be increase. So all these things has to be considered before selecting a tool material for certain application. Okay. Additionally, if you are selecting a cutting tool material, what are the parameters that you think of? The first one, the cutting tool material should be able to withstand high loads. High loads in the sense, the forces that are going to be generated in metal cutting. So the cutting tool material should be able to withstand those forces. That is the first requirement. Then it should maintain those properties, or it should withstand against same forces at elevated temperature also. Means if I say material has got certain toughness, certain strength, certain brittleness at room temperature like 26 degrees Celsius, same property should be maintained by that cutting tool at 600 degrees Celsius also. Okay. So it should withstand elevated temperature. The temperature I mentioned it 600, but that could be excess of 1000 degrees Celsius also. And at that elevated temperature also, the cutting tool material should not change its properties, the properties that has been referred while selecting the material. Then third one is severe frictional condition. There is going to be friction between cutting tool and workpiece, and that friction is going to result into temperature. And once that temperature has increased till a certain extent, it has got its own drawbacks. We know that at elevated temperature, the cutting tool material, workpiece material, both are going to get softer. And in that softened condition, that wear rate and all going to increase drastically. Additionally, increase in temperature is going to change the properties of the material, and that alteration of property may not be desirable all the time. And because of all these conditions, we need to select the cutting tool material properly. Now, there are certain specific properties that we need to consider. This high load, elevated temperature, frictional properties. In addition to this one, there are some specific properties. The first one is called as high hot hardness or hot hardness. Hot hardness means, as I said, at a room temperature, the material is going to have certain hardness value. And we know that as I increase the temperature, this hardness is expected to decrease, because material is expected to get softer with increase in temperature. So at elevated temperature, the amount of or the value of this hardness is expected, because even at elevated temperature the cutting tool shouldn't get softer, because it is expected to remove material from the work surface, not from the tool itself. Okay, so at elevated temperature, what hardness value cutting tool material have, that value is nothing but hot hardness, or in short, hardness at high temperature is nothing but the hot hardness. That is first. Second, high wear resistance. The cutting tool material should be removed from the work surface and not from the cutting tool surface. And this can be achieved with wear resistance. More wear resistance means less tool wear. So that way, wear resistance has to be there. Third one, high resistance to brittle fracture. Now, this is a important parameter, because we know that when you use a cutting tool to remove material from work surface, it is expected to be harder than workpiece. So we use cutting tool that has got more and more hardness. But with increase in hardness, there is going to be unavoidable increase in brittleness also. So if material is hardest one, it is going to be brittle one also. And brittle material, the wear resistance will be more, but while undergoing the machining operation, if there is some inclusion in the workpiece, that is some impurity is there, some hard particle is there, and when this hard particle comes in contact with the work tool, that is going to make cutting tool undergo a fracture. Additionally, if you are machining the workpiece surface and there is some step, that is workpiece has got multiple steps, and when you using a cutting tool to remove material from those surfaces, that sudden step in the workpiece is going to have a sudden impact on the cutting tool, and that impact loading will make a brittle tool fracture easily. And if you want to avoid all those things, that brittleness has to be controlled. So that way, high resistance to brittle fracture has to be there. Now, the difficulty is having all these properties with a single material is not possible, because if I increase the high temperature resistance of material and wear resistance of material, then there is going to be increase in brittleness of the material also. So that way, having all these properties with single tool will not be possible. So again, we need to be optimistic. We need to find some optimum condition where all these values are going to have some acceptable range. Okay. Next, now in addition to these things that are related to cutting tool, the cutting tool performance will be affected by these additional parameters. What are those parameters affecting the cutting tool performance? First one, relative hardness of the tool and work material. Relative hardness means we know that if I want to remove material from the work surface, cutting tool has to be harder. So the difference between hardness of cutting tool and workpiece is going to decide the performance of the cutting tool. That is but obvious, right? Second, abrasive particles such as scale on the surface of the workpiece. As I just said, if some hard inclusions are there or impurities are there in the workpiece surface, that impurities are going to be a cause for increased wear rate of the cutting tool. Additionally, scales on the workpiece surface. Scales means when you produce workpiece by using certain manufacturing process, there are chances that surface of the workpiece has got hardened because of the manufacturing process. There will be a hard layer on the workpiece surface, and that is called as scale. And that hard layer will be uh, affecting the tool performance. That is second cause. Third one, chemical compatibility of the tool and workpiece material, that we have explained several times, right? The chemical affinity should not be there at room temperature or even at elevated temperature. If that chemical affinity is there, then there would be diffusion of the work material from the cutting tool to workpiece, and there would be increased tool wear rate. Next, cutting temperatures. The temperature plays a vital role in the performance of the cutting tool. This one we have discussed all the things, that temperature, what temperature is going to cause to cutting tool as well as workpiece, that we know. Then condition of the machine tool and its rigidity, because sometimes when cutting tool and workpiece are mounted on the machine tools and the material is being removed, the forces generated might cause bending of the machine tool structure itself. And to avoid that one, we need to provide enough rigidity to the machine tool, and that rigidity decides the power consumption. Also, unnecessarily rigid machine is going to increase the cutting forces. That rigidity has to be optimum. That should not be very less, that should not be very high. So that also we need to consider. And last one, type of machining operation. Type of machining operations in the sense, suppose this is a workpiece, it is a cylindrical one, it is being rotated, single point cutting tool moving in this direction. If I start from this end and keep reducing its diameter, this is a plane turning. But suppose if there is a step over here, there is another step over here, then such a kind of steps are going to cause sudden increase and decrease in the cutting forces. And because of that sudden increase and decrease in cutting forces, the tool might undergo some failure, because there is sudden rise and sudden drop in the cutting forces. So that instantaneous loading will cause tool to undergo failure. So that also decide the performance of the cutting tool. Next, major classes of the cutting tool materials. Now, here, if you look into this picture, you will get overall idea of the cutting tool materials. The first one is carbon steel, then high speed steel, then cast alloy, carbides, polycrystalline, CBN and diamond, and then single crystal diamond. Now, uh, initially, when this material removal process came into existence, the tool used was this carbon steel, because that was the available material, or that was the most advanced material at that time. So that carbon steel was used as a cutting tool material, but that was having certain limitations. The this carbon steel tools were able to withstand against temperature of 250 degrees Celsius only. If temperature exceeds beyond 250 degrees Celsius, there was drastic change in properties of the carbon steel, or the carbon steel tools were not able to be used beyond 250 degrees Celsius. So that was causing limitations on the cutting speeds, because we know that if you increase the cutting speed, there is going to be increase in temperature, and if this temperature is to be held at 250 degrees Celsius, that cutting speed also has to be limited to that value. Now, after the carbon steel, the second material is high speed steel. High speed steel is basically a steel with certain alloying elements. When the manufacturing industry or the people related to all this field, they were not aware of the heat treatment process, or this heat treatment process was yet to be discovered. This heat treatment was discovered by Taylor, the scientist named Taylor. And before invention of this heat treatment process, the material used was a carbon steel. And when they came to know about this heat treatment process, they understood that the properties of steel can be improved further, and that improved steel is nothing but the high speed steel. Now, when they started using high speed steel, this limitation of 250 degrees Celsius changed to 550 degrees Celsius, because high speed steel were able to hold their properties, that hardness and strength and all, up to 550 degrees Celsius. So the speed that was available with 250 degrees Celsius now could be increased up to temperature of 550 degrees Celsius, or speed could be increased till temperature increases to 550 degrees Celsius. So, the high speed steel is the first material that help this manufacturing industry people to increase the speed of machining process beyond this carbon steel. And that's why the material itself was called as a high speed steel. Now, at the present situation, if you look at the machining speed available with high speed steel, it's quite low, because after that high speed steel, much superior materials came into existence, and with those materials the cutting speed could be increased like hundreds of the times, right? And because of that one, the speed available with high speed steel at the moment is not a high speed steel, but when it came into existence, that time it was a high speed. So the material is called as high speed steel. Okay. So that way, the materials came into existence. Now there are certain properties. The first one is hot hardness. Hot hardness means hardness value at a certain elevated temperature. When you increase temperature, the hardness is expected to decrease, but the tool has to withstand its hardness at elevated temperature also. So that value is important, and that hot hardness keep on increasing in this direction. Carbon steel has lowest value. After that, high speed steel, alloy steel, carbides, polycrystalline materials, and then single crystal materials. In the same direction, this wear resistance also increases, because hot hardness and wear resistance are related to each other. Harder the material, it will have more wear resistance. Now, compared with these two properties, the third one is toughness. The toughness plays an important role in case of cyclic loading, or the operations where we saw there are sudden changes in the dimensions of material, and that is going to cause sudden rise or drop in the value of cutting forces. And for such a condition, the toughness has to be there. But if toughness increases, this hardness value is going to decrease. And same you can see over here. The carbon steel is toughest one, whereas these diamonds and CBNs are having lowest value of the toughness. Okay, so that way the properties of these materials varies. Okay, here the relationship between hardness and temperature for all the materials that we saw over here has been shown. So here we can see that. Let's begin with the carbon steel. At zero or somewhere here at atmospheric temperature, it will have around 1000 kg per mm square of the hardness value, and when temperature starts increasing somewhere here at 250 degrees Celsius, there is a continuous decrease in the hardness, but beyond this point that increase is a severe one. So up to 250 degrees Celsius you can use carbon steel. Same in case of high speed steel, the working temperature could be extended up to 550 degrees Celsius. 600 over here, 400 over here. And you can see that graph or slope of that graph is increasing beyond this point drastically. So till that temperature, you can use the high speed steel. And similarly, these are the remaining materials. These are alloy steels, then carbides, then polycrystalline materials, and then single crystal materials. Now their values are, if you compare, if this carbon steel or high speed steel has got 1000, then the materials are having 6000 and beyond that. So that much hardness these materials can offer at elevated temperature also. If you look at the example of this polycrystalline diamond or polycrystalline CBN, the value at atmospheric temperature and value at around 800 degrees Celsius, that change is not that much drastic. Means if you can use cutting tool over here and you can use it at 800 degrees Celsius also with better performance. Okay, so that way the properties of these materials depends on the temperature, and because of that one those materials has that high temperature or high speed applications as well. Okay, now let's discuss individual material. Let's begin with the high speed steel. So as I said earlier, this high speed steel is nothing but a alloy steel. Now what are the alloying elements? The alloying elements are tungsten and chromium. Those two are the prominent elements. Out of those two, tungsten has got highest percentage, that is 18%, whereas chromium is about 4%. Now, in addition to those two materials, there are certain additional materials that would be there depending upon the particular property requirement. Whether you want to have material uh, better heat dissipation capacity, reduced friction between the cutting tool and workpiece, or material is expected to have certain hardness. So depending upon such a property, there would be certain additional materials. The additional materials would be cobalt, vanadium, and molybdenum. So all of the materials could be there, or some of them would be there, and their percentage would be also varying depending upon the property requirement. Now, what happens when you mix all these materials? When you mix this tungsten, chromium, and either of those three materials and heat that combination at elevated temperature, there will be formation of the carbides. There will be formation of carbides, and carbides are going to have or going to be much harder than the base material. So those hard carbide particles will form at elevated temperature, and they will be distributed all over the material. And because of that one, the hardness of material will be increased compared to base material. Now, when you use high speed steel, as I mentioned earlier, the temperature could be extended up to 550 degrees Celsius, or till 550 degrees Celsius, you can use high speed steel. Now, as I mentioned, the high speed steel were superior materials at that time, but now there are large number of advanced materials available out there, and if you compare properties of those materials with high speed steel, those materials are having better properties, so better machining performance. Okay, so nowadays high speed steel materials are prominently used in making drills and milling cutters, because in those two materials the whole uh, shank as well as cutting edges, everything has to be made with the single material. So in such cases high speed steel will be used. But even that milling cutters are being replaced nowadays, there will be a circular disc having uh, mounting arrangements made, and on which you can mount inserts. And if insert fails, you can remove it and put another new insert. So that way even these milling cutters are being replaced, but still that disc has to be manufactured by using these high speed steels, because that is expected to have or expected to withstand those cutting forces. Next is alloy cast alloy steels, or cast alloy tools, not steels, sorry, cast alloy tools. So in case of these cast alloy materials, the main difference is iron will not be there, because we know that steels and all the forms of steels are going to have iron as a base material. But in case of these cast alloys, the iron will not be there. So instead of iron, there will be different materials like cobalt, chromium, tungsten, carbon, etc. Those materials will be mixed together, heated to at elevated temperature. So there will be again formation of carbide phase, and you will have that final properties of the material. Now with these cast alloy tools, again you can increase the speed beyond speed possible with high speed steels. So whatever speed was possible with high speed steels, that can be further increased with the help of cast alloys. The application of these cast alloy materials are machining of cast iron, malleable iron, and hard bronzes. When you are machining these materials, you can go with the uh, cast alloy tools. Next, cemented carbide tools. Now, from the name, cemented means something has to be connected to some other part, right? So there will be one shank or supporting material, and to which we need to connect the actual tool. So that connecting could be either mechanical fastening, brazing, or some other process. But that has to be connected to a holding body. Okay. So in case of cemented carbides, it is basically a carbide tool So the raw material will be tungsten powder and carbon. Those two will be mixed at certain elevated temperature. That elevated temperature value has not been specified, but that would be some higher temperature in the range of like 800,000 degrees Celsius. And when this tungsten powder and carbon are mixed together, they will be added to cobalt. So that would be another major element of the carbide tools. And when all these are mixed together, they will be formed into the shape like these carbide tools, prominently manufactured in the form of inserts. Okay, so when all these elements are mixed together, it will be shaped in the form of insert and then heated to a temperature of like 1400 degrees Celsius. So that would be a further increased temperature at which they are compacted. So at 1400 degrees Celsius, when it is heated, it will gain its final properties like hardness, strength, and all. And like previous materials, like steel was able to withstand up to 550, alloy tools were uh, possible to have certain elevated temperature. In case of these carbides, the working temperature could be 1200 degrees Celsius. So up to 1200, you can easily use these tools. There will not be a drastic change in properties of these tool materials. So if 1200 temperature is there, you can increase the cutting speed further higher. So you can use uh, again, you can increase the cutting speed with these carbide materials. And as I said, these carbide tools are usually used to made inserts, and then those inserts will be braced or clamped on the tool holders or some holding body that will be used to hold that cutting edge. Now, in case of these carbide tools, we know that these materials are strongest and having a better wear resistance, because that 1200 degrees Celsius temperature is not like a regular temperature. If it can with a it can useful, or if it is useful at that elevated temperature, it must have that strength and wear resistance, right? But when you use this material to machine steels at elevated temperature, there is a considerable crater wear. Now you need to remember that crater wear. What is crater wear? The wear form on this rake face is crater wear, and wear form on this flank face is the flank wear. So this crater wear will be considerable in case of machining of the steels. Now, to avoid this one, what we usually do in these carbide or carbide materials, there will be addition of tantalum carbide or titanium carbide to reduce that crater wear. So what happens when you use tantalum carbide? The product material would be tungsten tantalum carbide, and if it is titanium, then it would be tungsten titanium carbide. And using either of those two combinations, you can reduce that crater wear in case of steels. Now, initially I mentioned that the tungsten and carbon are the first two materials that will be mixed together, and then this will be added to cobalt. Now the amount of cobalt decides the toughness of the material. If you increase the cobalt content, toughness will increase. If you decrease the cobalt content, toughness will decrease. But we know that increasing toughness decreases the hardness and hot hardness. So that also we need to consider. So depending upon the application, you can decide the cobalt content. But remember that cobalt is to decide the toughness. And as these carbide materials are having hardness and hot hardness values much superior than previous material, but there is a brittleness also. So un sorry interrupted cuts need to be avoided in case of these materials. Because of hardness, if there is sudden increase or decrease in the cutting force, they might undergo failure. Okay, so this is all about cemented carbide. Next one is coated carbide. Now the base material is this carbide material only, but from the name itself, you can easily get that something is being coated on the carbides, right? So when the these cemented carbide materials are required to have more hardness, we know that the cemented carbide itself has got a better hardness value. But if you want to further increase that hardness value, we know that if you increase hardness of that base material, the brittleness is also going to increase. That is but obvious, right? So what we do usually when you want to increase hardness of these carbide materials, instead of increasing hardness of that whole material, we simply coat the carbide surface with another layer of material which has got hardness more than these cemented carbides. So what will happen? The base material brittleness will not increase because we just have coated layer of hard material over the ceramic surface, or that sorry, over the cemented carbide. So the layer has got hardness value more compared to base material. So base material hardness and brittleness will remain unaltered and you will get more hard surface. The same thing you can do to achieve some additional properties also. Like when you want to have better thermal conductivity, when you provide lubrication between cutting tool and workpiece, you can coat the surface with such a material. So that way you can improve the properties of material by providing coating on the base surface. So that way you can improve the material properties without altering properties of base material, so that its strength and all will remain unaltered and you will have better property surface also. So usually what we do, we coat the material with a layer of thickness around 5 to 8 micron. So that small layer will be there that will be applied on the base surface and that will have better properties. Now to apply this layer, usually we go for chemical vapor deposition process, normally called as CVD. There is one more process that is called as physical vapor deposition process, called PVD also. But for coated carbides, the process applied is chemical vapor deposition, that is CVD. So when that coating is there, you will have better machining performance. But once that coating has worn out, because if this is base material and if I have applied some 5 to 8 micron layer on the base material, if that layer is gone and if that base surface has got exposed, again the wear rate and all are going to be same as that of the base material, because now that layer has gone and base material has exposed. So as long as coating is there, you will get better machining performance, and once that coating has worn out, it will act like a basic carbide material. Next, ceramics and cermets. The ceramic is also called as cermet. So ceramic and cermet tools. Cermets are basically a natural ceramics, and there are certain ceramic materials like alumina, Cylon, silicon nitride, and all that we manufactured. We manufacture, or those are the uh, manufactured by mixing raw materials to have that desired properties, or to have some specific properties. So that are like synthetic ceramics. Synthetics or artificial that we make in industry. So those are advanced or industrial ceramics, and ceramides are natural ceramics. Now when you look at the basic manufacturing process employed for the ceramics is, we take raw material, we mix them together, we form them desired shape in that wet form, and then we heat it to a elevated temperature so that you will get the final product. Now just like carbides, in case of ceramics and ceramides also, the properties that you have got after final sintering. Sintering is the heat treatment process. When you heat it to get the final properties, and once you have got the product, the properties cannot be changed, like in steels and alloys and all, where once you have got the product, if this is a product that has been manufactured, its properties can be altered, as well as its dimensions also can be changed, because you can remove some material and you can reshape it. But in case of ceramics and ceramides, these things are not possible. Once the product has got manufactured, its properties, its shape, its dimension, nothing can be changed. Okay, and because of that one, the tools manufactured from ceramics are usually throw away inserts. So when you use that insert, if this cutting edge is gone, you will use this cutting edge, and when that all the cutting edges of the insert are gone, you can simply throw it away. Okay, you need not to regrind, reshape anything. So that scenario would be there in case of these ceramics. Now the prominently used ceramic materials are alumina, Cylon, and silicon nitride, Si3N4. Now, if you compare the properties or their application situation, the alumina, the machining performance that you can get with this alumina, the Cylon will have better performance compared to this Al2O3, and Si3N4 will have better hand compared to Cylon. So it's like Cylon is superior than alumina and silicon nitride is superior than Cylon. So that way you can think of their application areas also. If you discuss that in detail, you can see here aluminum oxide is most common, perform best finishing and semi-finishing operations with non-interrupted cuts. So there should not be interrupted cutting on the workpiece. If that interrupted cuts are there, alumina has got brittleness more compared to Cylon and silicon nitride, so it will fail easily. Okay. Now, if you want to avoid this limitation, you need to go for Cylon because it offers greater resistance to mechanical shock. So the mechanical shocks that could be there because of that interrupted cuts and all, Salon can take better care compared to alumina. Okay. Now the limitation with Salon is Salon cannot be used with carbon steels. So when you want to machine carbon steels, this Salon will not be a choice. The reason is again there is a compatibility issue between those two. Those two are going to have chemical incompatibility, or there would be certain reactions taking place either at room temperature or at elevated temperature, and that will cause excessive wear on the cutting tool. And because of that one, when you machine steels, Cylon should be avoided. Now last material is silicon nitride, and it has got superior properties compared to alumina and Cylon. So silicon nitride tools have some properties are similar to Cylon, but additionally improved toughness, and because of that improved toughness, it can withstand high temperature and high loads compared to Cylon. So you can simply see the properties gets improving from alumina to Cylon and Cylon to silicon nitrides, and accordingly you can think of the applications as well. Next one is polycrystalline tools. Polycrystalline tools are basically CBNs and diamonds that are manufactured artificially. We know that you can get diamond in nature also, but the diamond that you got in nature will be a single crystal diamond. And if you compare the properties here, this is line for single crystal diamond, and this is line for polycrystalline diamond. So this is artificial one and this is natural one. So you can see single crystal diamond has got better hardness value compared to polycrystalline diamond. If it is so, then why we need to go for polycrystalline diamond? Because single crystal diamond shows better properties than polycrystalline, right? The reason is this single crystal diamond, whatever properties it has got, those properties will not be uniform, because it is the crystal is formed naturally. That crystallization will not be uniform. In one direction the properties would be different, and also that property would keep changing as you switch from one point to another. And because of that one, when you use that single crystal diamond as a cutting tool material, the performance that you will get will not be predictable, because those properties are not uniform in nature. And because of that one, we go for the polycrystalline diamond. Now to make polycrystalline diamond, either we use natural diamond particles or artificial diamond particles. Those particles will be compacted at high pressure and high temperature. So those particles mixed with binding materials that would be compacted, and that compaction will be uh, taking place at high pressure and high temperature. So that at higher temperature and temperature, that binding material will form bonds with the particles, and you will get the final product. Now if you compare the let's not discuss about the diamond, because diamond is the most expensive one, you can easily get that. But if you compare the CBN, that is cubic boron nitride, if you use even cubic boron nitride over the carbides, the cost of CBN will be almost 20 times higher than the carbide. So it will be 20 times more costly compared to carbides. So when you want to use this CBN tool, you must consider this cost also, because you need to pay 20 times more money for that material, right? But when you use CBN, the tool life could be 50 times longer than carbide. So if you can justify that cost, you can go for the CBN. And if that cost is not justifiable, then you can continue with the carbide, because you can easily see that the cost is 20 times higher, but life is 50 times longer also. So that way, the scenario would be there in case of these polycrystalline tools. And again, these polycrystalline tools are going to be in the form of inserts. So this is the actual tool or insert that has been made. This whole shank will be made up of some other material, and there will be arrangement where you can fix this insert, and you can use this cutting edge, this cutting edge, this cutting edge by rearranging its position. And once all the cutting edges are gone, throw it away and install the another cutting insert. So that insert could be provided with central hole to fix it on the shank, or you can use this kind of arrangement also. Okay, so this is for uh, polycrystalline tools. Okay, here we are done with tool material parts. Next one, the work material machinability. Now this concept actually we have discussed several times in the past. Machinability means, if I consider this is a raw material that has to be converted into some product. So for that one, here I am going to use some manufacturing process. And as we are talking about material removal processes, this manufacturing process is going to be material removal process. That process will remove some unwanted material from the raw material, and it will convert this raw material into a product. Okay. So now when you convert a raw material into product, this product is expected to have certain properties. Additionally, when you use that particular material removal process for conversion of raw material into product, there are certain properties associated with this machining process also that we need to consider. So some properties related to product, some properties related to process. What are those properties? Material removal rate, surface finish, tool wear rate, accuracy, material properties. Like you can think of some additional properties. Now, when you convert raw material into a useful product, this these properties associated with machining process and product itself has to be within acceptable range. Acceptable range means material removal rate should be there, because that is going to decide the production rate, right? Surface finish, because that is going to decide accuracy or life of the product. the tool wear rate, because frequent regrinding or replacing of the cutting tool is going to cause that economical loss. Also, production rate will fall if cutting tool is being filled frequently. Accuracy, then material properties. If during machining temperature increases beyond range, it is going to affect the properties of the material, and that may not be desirable, right? So such a properties or combination of such properties has to be within acceptable range. And if all these properties are as per requirement, or if all these properties are optimum, then the raw material which is being converted into product by using that particular material removal process, we can say now the machinability of this raw material is good. Okay. And if this material removal rate is not as per expectation, surface finish that we are expecting, we are not able to get, tool wear is more prominent, or we are in a need of frequent regrinding and replacing of the cutting tool, accuracy is not as per requirement, there is alteration of the properties of material, or there is formation of some hard layer on the workpiece surface, or there is cracking of the workpiece surface because of heating and cooling cycles. If such a things are there, then machinability is poor, right? So that way you can discuss this machinability concept. Again, this concept is purely dependent of the application. How it is dependent of the application? Let me discuss. If you are machining, like, let me take one high class example. If you are machining aluminum material to generate a mirror, these are used in space industries, so those are going to be extremely costlier also. So when you machine aluminum to generate a mirror, usually to machine these, diamond tools are used. There is a dedicated process for this one, that is called as diamond turning. So in that case, you need not to worry about the cost, you need not to worry about the production rate. Why? Because the cost of this product is extremely high, so let it take longer time, that is not going to be thing to be bothered, right? But what we need to bother, we need to be bothered of accuracy, we need to be bothered of the material properties that might change, right? So in case of this particular application, machinability is nothing but accuracy and material properties. The material removal rate will not be a part of my machinability now, right? Surface finish would be there, because surface finish is nothing but the accuracy. Tool wear, I just need not to worry because it's a diamond, right? And the material which is machined is the softest material, one of the softest, right? We are machining aluminium by using diamond, so tool wear is not going to be there. So can do I need to think of tool wear? No, right? So that way, the concept of machinability is purely based on a application. Application changes, the machinability concept will be changed, right? So somewhere material removal rate will be important, somewhere tool wear rate will be important, somewhere accuracy will be important, somewhere something different would be there. Okay. So that way this machinability concept has to be discussed. So clearly, the term machinability can have little meaning except in loose qualitative sense. Qualitative sense in the sense the things that we just discussed. Any doubt, any query, anything need to be explained in further details? Let me know. Next thing is tool quotings and all that will begin in the tomorrow's session.